Welcome to part 5 of our chapter 29 lectures on intermediate physics. We're talking about magnetic fields. Where we left off with last one was talking about the Lorentz equation. So the Lorentz equation has to do with a charge Q moving into an electric field that is going to feel a force that's given by the first part of this equation. So the force a charge feels in an electric field is just given by Q times that electric field. It's going to be in the same direction as our electric field if the charge is positive, in the opposite direction if the charge is negative. So the Lorentz equation has to do with both this force and the force a charge moving in a magnetic field. So a charge moving in a magnetic field feels a force that is Q times its velocity crossed with that magnetic field B. So all we're doing right here with the Lorentz equation is really a Newton's second law thing. We're taking the sum of all our forces and seeing what that does to our particle. So the sum of all our forces is the force due to the electric field and the force due to the magnetic field. So this image over here on the right side, this is what you would call crossed fields. So the reason it's called crossed fields is if you look at this image, your magnetic field is going into the page while your electric field is going from the top plate to the bottom plate on that page. So they're at right angles to each other. If they're at right angles to each other, a charge Q that enters this field with a certain velocity is going to feel those two forces. So it's going to feel the electric force. If it's a positive charge, it's going to feel the electric force downward, as it's drawn in the second part of the picture here on the right-hand side. And if it's a positive charge, it's going to feel a magnetic force upward from that magnetic field going into the page. And again, check your right-hand rule with this. Point your little fingers in the direction that our charge is moving. Rotate your hand around so that your fingers will bend normally in the direction of our magnetic field, which is into the page. And you'll see that your thumb points upwards, right? So you can double check that. So the Lorentz equation is just this equation that I have boxed over here on the left-hand side that tells us how a charged particle is going to feel forces due to an electric and a magnetic field. Now, what's interesting about this charged particle is that depending on the speed it's going or the charge it holds, right? Speed is probably the easiest thing to change. So depending on the speed it's going, that force could balance out, or it could cause our particle, if V is too strong, to be deflected upwards, or if V is too slow, to be deflected downwards. Okay, so that means there are some applications for this crossed field idea. One of the applications is what's called a velocity selector. So a velocity selector lets you basically choose what speed of particle you are going to allow to pass straight through and come through this slit on the other side. So some electronic devices and experiments need a beam of charged particles that are moving at nearly the same velocity. This can be achieved using both a uniform electric field and a uniform magnetic field, arranged so they are at right angles to each other. So what we want in a velocity selector is we want to sum up all those forces this charge is feeling, and we want no deflection. So we want the sum of those forces to be zero, right? Deflection would equal an acceleration, right? Because acceleration is not just change in speed, but change in direction. Okay, so if we want to add up those forces and have them equal to zero, that means we want QE added to QV crossed with B, whatever the result of that is, to be zero, right? So QE, QV, QB, these are all, they're all vectors, right? So we need to pay attention to directions here, and we want it to cancel out in every single direction, which is why we have that crossed field. So if we are moving so that we have a crossed field, and that our velocity is at right angles to our magnetic field, that means we are going to put all of these in the same plane. And you might decide that, say, downward is your negative direction, right? So what I'm doing here is I'm using the same kind of explanation we had over here, where B being in our force due to the magnetic field being in the positive direction, and our force due to the electric field, and what I'm defining as the negative direction. That's where the sign change comes from. So I want those to equal 0. So I want them to be equal and opposite, basically. Which means for my velocity selector, I need this to be the case, and I need them to be in the same direction for this to be true. So you can see Q cancels out. It doesn't matter what Q is. And my velocity selector just lets me know that my velocity is going to be a ratio of the magnitude of my electric field and the magnitude of my magnetic field, right? And so this is for the very specific case of crossed fields where everything's at right angles. My velocity is at a right angle to my electric field, which is at a right angle to my magnetic field as well. So that's one application of this, is the velocity selector. All right, so I wrote all this stuff in the previous slide. There's more space for you to see what I was talking about there. So another thing we can see with our force on a current or a force on a charge is that you can have torque on a current loop. So again, we've got to circle back to some physics 1 knowledge, and remember that torque is a force applied to a lever arm. So you need to define a lever arm. Here we've defined the point of rotation as being halfway across this arm B. So this is our lever arm, and since it's a cross product, right, that means that it becomes simple multiplication when those things are at right angles. So if we've got a current that's moving up on this left-hand side of this current loop, that current, again, take your right hand, that current in a magnetic field, so I is going to be the direction we point our fingers. We want to rotate our hand around so that our fingers naturally bend in the direction of B here. So when we rotate our hand around, we're going to see that the force is into the page, as denoted by that X. So since that's at right angles with this thing we've defined as the lever arm here, the torque on that left-hand side that we'll just label with a 1 is the force there times the length of our lever arm, which is just half the length of that B length of the current loop. So the force, since we're at right angles again, becomes this really simple I times A times B. That just has to do with the length of current that's in the magnetic field, which is, I've drawn all over it, let's erase it for a second, which is this length A here. And then times B times the strength of our magnetic field. So force times our lever arm. Now we've got 2 sides. If you do the same kind of right-hand rule here on the right-hand side, you will see that the force would be out of the page because our current is going downward on this side. And again, point your fingers in the direction of current, rotate your wrist around so that your fingers bend naturally in the direction of the magnetic field, and you'll see that your thumb would point out of the page. Okay, so we add those together to get our net torque, because remember, net torque is just add the torques, right? So when you do that, you've got IA times that capital B, the strength of our magnetic field, times our lowercase b, the width of our current loop, divided by 2. We do that twice. So it turns out if we've got this lowercase a times this lowercase b, that is just our area of our current loop, right? That is just this whole, in this case, box, this whole rectangular area. So we've got I times area times b. Now, if we have more than one loop of wire, we'd have more than one instance of current, and so we'd multiply our force by that more than one instance of current. And so if you have, say, n number of loops of wire, you have a net torque that is your n number of loops times the current going through them, times the area described by them, times your strength of your magnetic field. Now, again, we switch this to simple multiplication for our force, but if you make an angle with B that's something other than that 90-degree angle, your lever arm changes or your force changes. You can look at that either way. And so our net force is going to need sine of that angle theta that your coil makes with B. Okay, so what that really means is if you've got sine of an angle, you've got to describe it with a cross product instead, or you can describe it with a cross product. Now here we've assigned our vector quantity to A. That, if we look down here at the bottom, is the area, the normal of the area, using the right-hand rule. So over here on the right in my little drawing example, if we take our right hand and point it so our fingers curl around in the direction of current, again, right-hand rule, our fingers curl around in this direction of current, our thumb would point downward into the page, right? So I would draw an X indicating that my thumb's pointed downward into the page, and that's the direction of the normal of this area, right? Okay, so that lets us define one more thing, this mu with a little arrow, right? So it's a vector, is our magnetic dipole moment of any coil of wire. If we've got n turns of wire, it's n times I times A, so that area described by the wire. And again, the direction of our area is the normal, so it's going to be perpendicular to the plane that that wire is sitting in. And we're going to use that right-hand rule to figure out, is it into the page or out of the page in this case. Okay, so here is an example with torque on a current loop. So here I've got a circular loop. I've got it described on the other page. I've got a circular loop with a radius and 10 turns of wire, and we're going to figure out the torque, right? So here's a top view of what you would be seeing of this thing on the previous page, right? Where you're seeing that axis of rotation, that lever arm that I described with a B/2, right, and all that good stuff. So let's do an example of that because that's probably more useful to you guys. So we've got a circular coil of wire, we've got a diameter of that circular coil, and we know that it contains 10 loops. The current on each loop is 3 amps, and the coil is placed in a 2 Tesla external magnetic field. So we want to determine the maximum and minimum torque exerted on the coil by the field. Okay, so let's write down all the things we're given, what we know, what we're trying to find out, right? So we're given, I'm just going to use my highlighter for all this. We are given that we've got a circular coil, so that's going to help us with our area. We've got a diameter of that coil, and we've got a number of loops that it contains. We've got current, we've got an external magnetic field. Okay, we want to find maximum and minimum torque, so we want to find two different things. So we are given, whoa, that's a thick pen. Let's try that again. We are given that our area is circular. So we would use pi r squared for area, right? Well, we're actually given a diameter, so I'm going to rewrite that we're going to have to take our diameter and divide by half and square it. Okay, we are given that diameter of 20 centimeters. I'm going to switch to meters because that's what I do, right? I get into my standard units. We are given that we've got 10 loops. Current is 3 amps, that's standard. and our external field is 2 Tesla. We want maximum and minimum torque. So if I circle back, I know that the magnitude of my torque is given by N I A B sine of 0. The maximum torque is going to be when that sine function equals 1, right? Our sine function can go between -1 and +1. So our maximum torque is going to be just a simple NIA and B. So I'm going to substitute in for my area. I'm going to use my N, my I, and my B that were given. If I do that, I get a maximum torque of somewhere around 1.51 times 10 to the minus 2 Newton meters, right? So that's my maximum. My minimum torque is going to be actually going to be when sine equals 0. It's going to be 0. So here's my max. Here's my min. Circle those answers. Right? And that's an easy example of our torque on a current loop. So you can do more examples where you're like tilting the loop, so you're applying a force that goes against gravity and actually lifts it up off the ground. You can do all kinds of other examples with your torque like that. So we want to actually figure out that what is our potential energy principle for our rotational moment. So if we have a torque that's not 0, we're going to be doing work, right? So the potential energy of a magnetic dipole in a magnetic field is going to be given by the torque that happens as you rotate that thing through the field. So if we write in our equation for what torque is for our loop that's getting rotated in this field, we can write it in this way. So the work energy principle says, all right, we do that work through a certain distance. So before we've been writing force through a certain length that we've moved. This is just a rotational expression of that same thing, right? Okay, so our torque, we write down our thing. If N, I, A, and B are all constants, they can come out of that integral. And we're just doing an integral of sine theta d theta. That integral is really simply a negative cosine theta. Because we didn't have any limits of integration, we have this extra constant of integration. And here, I've just substituted in our expression for magnetic dipole moment, which is n number of loops with I amount of current that describe an area A. So if we choose, our minimum spot for our amount of potential energy to happen when you are at a certain angle, you are going to basically choose your constant of integration to be 0, right? So when we do that, we see that it describes something like this. So the potential energy of our current loop in a field is given by this dot product. So cosine, remember, has to do with dot products. And remember that our magnetic dipole moment is described by this area. So if we have a current loop like this that has current going in this direction, I would again curl my right hand around that, and I would figure out that this area has a normal direction that is pointed up, right? So that's how we find out the direction of our area. And then if I put this thing in a magnetic field like this, so let's make our magnetic field look like that. Then I would need to find the cosine of the angle between these. So we go from our normal down to our magnetic field, since our magnetic moment is first in that thing, in that equation. And we would find that that's the angle between our normal and our magnetic field. It is something other than 90 degrees. If it is 90 degrees, cosine of 90 is 0, right? And so that potential energy would be 0 at 90 degrees and would be maximized when those two things are pointed in the same direction. Awesome. All right, this seems like a good place to pause. We'll pick up here with the next recording.